Yes, hi, good morning. My name is Maher Agassi. I'm with the Pure Aqua Inc., Santa Ana, California. We are here to present this webinar about the industrial reverse osmosis systems, brackish water source. We're going to talk about the main components that any industrial reverse osmosis systems would have, and the application that we can use this reverse osmosis system with. A typical reverse osmosis process would include the main reverse osmosis, and before that there is something called pretreatment, and after that there is something called post-treatment, as we see here. The main benefit of having a pretreatment for any reverse osmosis system is to protect the membranes from fouling, and that would prolong the life of the membranes and make the system perform in a very optimal way where the membranes would live and survive for a long time. Rejection would be better. The quantity of water would be according to the design. Now the system would suck the water from a storage tank or from a well or from point of use to feed it to the filtration system. Now, sometimes we need to dose a little bit of chlorine to get rid of the antibacterial presence or viruses. And if there is any heavy metals, we need to change the heavy metals from the dissolved format to a physical format where it's oxidized. The reason why we want to do that, because if it's dissolved, the media filter would not be able to capture this heavy metal. Example, the iron and the manganese, changing the form of the iron and manganese from dissolved matter to a physical matter would make it easy for the filters to reject or filter those two elements. The other application of the multimedia filter would be reduction of suspended solids. We cannot feed high suspended solids to the membranes. That's going to foul the membrane. Now, suspended solids is measured in milligram per liter or parts per million. Before the media filter, we should not go higher than 20 to 30 milligram per liter. So after that, it's going to be acceptable to the reverse osmosis after the media filter. And another definition, like where membranes manufacturer would like to have the water quality as a turbidity to be less than 3 SDI. SDI means silt density index. So if it's higher than this, it's going to cause a lot of problems for the holes or the openings of the membranes. Now, most of the membranes company, they would want the OEMs to bring down the quality of the water to less than 3 SDI. After we fed the water using the feed and backwash pump and then we dose some chlorine to the water, we pass the water through the multimedia filter. Now the water is ready and it's filtered, free of any suspended solids, and we reduce a big amount of the iron and manganese, and we got rid of the organic matter. Now we have some excessive chlorine still after the media filter that we have to get rid of it. That's why we do some chemicals, like using sodium bisulfite to kill the extra chlorine that we don't need anymore. If we pass the water without getting rid of the chlorine to the membranes, that's going to cause a major damage to the membrane. Like most of the membranes that we see in the market right now, they should not handle more than 1,000 hours based on 1 ppm of chlorine. So that means if it's going to be if the water has more than 1 ppm for more than 1,000 ppm for more than 1,000 hours, that's going to damage the membrane. The way you notice that the membrane is damaged, you're going to start a lot of leaking of the quality. That means if the membrane is producing 20 or 30 ppm, you're going to start seeing the quality of the water is going down, and it's going to start also passing more water. That means if it's giving 100 GPM, you're going to start seeing more water coming out of the membranes. Now it's time to dose what we call the antiscalant. Like Pure Aqua has its antiscalant, which is the PA0100, which is very good antiscalant against calcium and magnesium for all the carbonates and the sulfates. It's also good for the silica, and it helps if there is any traces of iron and manganese. Antiscalant, basically what it does is it makes the surface of the membrane smooth, slippery. When it's slippery, that means the calcium and the magnesium will not stick on the surface of the membrane. Now, the good thing is, like the antiscalant, it's NSF approved, and whatever excessive of this antiscalant is going to go to the reject side. So there is no chemical that's going to go to the product side. So it is, of course, it's NSF and it's safe for drinking. Now we're going to talk about the main core of the system, which is the reverse osmosis system. The reverse osmosis systems usually has like some instruments like the inlet valve, the flowmeters, the pressure switches, the pressure gauges. So those are all instruments are placed in the system, so it makes the operation smooth and fully controllable using the control panel. Now the first component is like the inlet shuttle valve. The inlet shuttle valve is responsible for controlling the feed water that comes to the RO. So when the system is running, that valve is going to be open. When the system is off, that valve is going to be closed. So there is no water that's going to pass through the reverse osmosis system. After the 5-micron filter, so we're going to have the high pressure pump, which is responsible for creating the osmotic pressure. That means the higher the TDS, the higher pressure that you need to pass the water through the reverse osmosis membranes. Now, the reverse osmosis membranes, they're like installed inside something called pressure vessels. Now, it depends on the capacity of the system. Some systems, they would have one pressure vessel. Some would have 2, 3, 4, 5, all the way maybe up to 60 or 70 pressure vessels. So it depends on the size of the system. There are like different designs. Some of them like single stage, some of them 2 stages, some of them 3 stages. It depends on the design, and all depends on the feed water characteristics. Lastly, the post-treatment that comes like after the reverse osmosis, more or less all depends on what is this water is going to be used for. If it's for drinking and we're going to store it, it's a good idea to dose a little bit of chlorine and neutralize the pH to bring it up to around 7. The same thing, like there's another way, like if you want to increase the pH, what do you want to neutralize the pH using no chemicals? It's a good idea to use the calcified filter where it neutralizes and raise the pH a little bit, where it's becoming very close to a pH of 7. Now, if the use of the reverse osmosis water is going to be without storing, or if the storage tank is for like a couple of hours, wouldn't be a bad idea to use a UV sterilizer after the reverse osmosis, where in case if there's anything like virus or bacteria in the piping, that would the UV would take care of it. Now we will start talking like about some of the components that we need to know whenever we want to design a reverse osmosis system. I mean, like, I know maybe this form is a little bit scary, but we don't need all this information, honestly. The most information that we would require, of course, we need to know the pH, we need to know the temperature, we need to know the conductivity or the TDS. And I would always recommend that make sure that you give us iron, manganese, and silica, because those are major foulants that cause problem for the membranes. Another thing that we would like to know, like some information, if the water is coming from surface water or shallow well, it's a very good idea that we know the nitrate. That would give us an indication if the water has some viruses or bacteria. The other thing that we would like to know, if the water is coming from city water, we want to know the level of chlorine in the water so we can design the sodium bisulfite dosing system that would get rid of this chlorine. Other things that we'd like to know, if we look at it here, we want to know the feed water source, if it's a well, surface water, or it's coming from the city water. It's also important to give us an idea how expensive or cheap is the water. So if the water is really expensive, we would optimize the system and go on a higher recovery design. There is no need for like any hot water application here, unless like the RO system is used for beverage industry or pharmaceutical, where they would require hot water sanitization. So usually we don't need to know the hot water if it's available or not. Now, other thing that we would like to know is the available water. I mean, like you might tell us that I would like to have a system that produces about 100 gallons per minute, while you don't have water to make up like for that system. Like the system, the RO system, to produce 100 gallons per minute, let's assume that the TDS is 5,000, we need at least 130 gallons per minute feeding the RO system, because like let's assume that we are working on an 80% recovery, so we need to have like about 25% more water than the produced water to make up for the overall water, and that's what makes up the recovery. So you need to know, like let's assume the recovery is about 80%, and we're feeding the system about 100 GPM. That means the system is going to produce 80 GPM, and 20 GPM is going to go to the drain. Now, the wastewater, which is the wastewater that's coming out of the RO, we need to know like if there is any discharge, wastewater discharge limitation. So, because sometimes the city would tell you have certain amount of water, like not more than 100 GPM, not more than 200 GPM. We also need to know like if there is any limitation of the TDS and chloride and all those things. Now, product water. Let's talk a little bit about the product water. It's important. So, like sometimes, like any manufacturing facility or like any facilities for drinking water or for like small towns. So we would like to know like what's the daily consumption and if there is any peak hours. We need to know like the peak hours flow rate, like because that might be 30 or 40% of their daily consumption. We also need to know if there is any storage tank. After that, we also need to know if there is any back pressure on the system. How high is the storage tank? So those information would help us to design our system efficiently without any problems. Now, since Pure Aqua manufactures RO and water treatment systems worldwide, it's important that we know the power, like what is the voltage. Like here in the US, we have 460 three-phase or 208 three-phase. The low voltage is, which is a single phase, is 110 or 115. In Europe, they have about 380 to 415 for the three-phase, and they have 220 volts for the single phase. So it's important that we know the frequency, and it's important to know the low and the high voltage. Now, it's also important that like when you require a system, you want to make sure that you have the area that's going to fit that system. As an example, like if the system would require about 100 by 75 feet area, so we want to make sure that you have this area. So it would be a very good idea that you share this information with us. Is there any question?
So far, so good.
Okay. Now this is like a typical process flow diagram for like a small industrial system or brackish water reverse osmosis system, like what we explained. Water is coming from the source, whether it's a well water, whether it's a tank, whether it's a surface water. Before it goes to the tank, there is a little bit of chlorine that's going to be dosed. Then we usually assume there is about at least 20 minutes of contact time between the water and the chlorine. So the chlorine would do a good job with oxidizing the iron and the manganese and getting rid of the viruses and the bacteria. After that, if the water is coming from well or tank, from surface water, we said it's going to go to a tank. If the water is coming from a city water, that means you're going to skip that tank and you're going to skip that chlorine and you're going to skip that feed pump, because the water is already pressurized and has between 40 to 70 psi. So the pressure is sufficient to pass through the meter filter and goes to the reverse osmosis system. Like what we explained, now the water is chlorinated and has oxidized iron and manganese. Is going to pass through the meter filter and get filtered. Then we're going to do antiscalant and dechlorination chemicals, and then we're going to pass that water to the reverse osmosis system. This is like the post-treatment, which is post-chlorine and post-pH. Now it depends on the application. The water might be stored in a tank and might be used directly. And we do not recommend any back pressure that goes back to the membranes. So the membranes do not like back pressure. After that, there is like some distribution pumps that's going to distribute the water to the different points of use. Now, as we explained, we already talked about the well water that has sometimes microorganisms and bacteria that can form a biofilm on the membrane surface. So that's why it's a good idea to get rid of this bacteria and microorganism before it goes to the reverse osmosis. And remember something, it depends on how high is the microorganism, so that the dose of the chlorine can go up to 2 to 3. Most of the time, it shouldn't be more than 1 milligram per liter. And like what we said, it helps to oxidize the heavy metals. Now this is a typical picture of a meter filter where it has 5 different valves. The benefit of any multimeter filter would reduce the turbidity and suspended solids, like what we explained, removes silt. The silt is a very fine dirt that passes most of the time through the cartridge filter. So that's why it's a very good idea usually to have a meter filter to get rid of the silt. Silt, like what we mentioned, most of the membranes company, they want to see the silt density index lower than 3. Now, like the filters, like what we mentioned, it has 5 different valves. The feed water are going to go from here. When the feed water when the process of the filter is going through the filtration mode, that means this valve is open, this valve is closed, this valve is closed, and this valve is closed, this valve is open. That means the water is going to go from here, goes inside the filter, penetrates through the different layers, and come back from the bottom, and then come back as a filtered water from here. So the inlet from here, the outlet from here. Now the next cycle is the backwash. Backwash is required when the filter is running for hours and hours and hours. It's going to block a lot of suspended solids. That means the differential pressure between the inlet and the outlet is going to start increasing. That means it's time to backwash the filter when the differential pressure reaches about 10 to 12 psi. 10 to 12 psi means if we measure the pressure that's feeding the filter and measure the pressure that's leaving the filter, if the difference is about 10 to 12 psi, it means it's time to do the backwash. The second cycle is when there is a backwash, this valve is going to be closed. That's the inlet water for the backwash. The reason why we have a separate valve is you can use the same city water or the same as the feed water, or if you want to use a separate filtered water. So you can have a different source of water to backwash the filter. So that valve is going to be open, that valve is going to be closed, that valve is going to be closed, that valve is going to be closed, and that valve is going to be open. The water is going to go from here, from the bottom. It's going to lift up the media take all the dirt and the suspended solids that are accumulated inside the filter and push it out to that valve, and that valve is going to send the water to the drain. The third cycle is the rinse cycle. The rinse cycle is exactly like the service water, where the water is being fed from here. So this valve is open, this valve is closed, this valve is closed, this valve is closed, and this valve is open. The benefit of having a short rinse cycle, when I say short, it's just 1 to 2 minutes, because we all understand the water is expensive, so we don't want to waste a lot of water. So it settles the different layers of media back to its position, and if just in case if there is any accumulated dirt, that will be sent to the drain before we send the water to the reverse osmosis. Now, those are the 3 different layers of the media filter. Usually, like the anthracite is in the top, the sand is in the bottom, and different layers of gravel in the bottom. Now, this is like, it just shows you how the water goes inside the filter, that passes through the anthracite, then goes to the sand, and then goes to the gravel. Gravel would protect the underbed distribution system. The sand itself is the filtration media or the filtration bed. So the bed or the filtration layer that does the filtration is the sand, not the anthracite. The benefit of having the anthracite on top of the sand, because like any time when the filter is on and off, that's going to trigger all the accumulated suspended solids on top of the sand layer to get distributed everywhere. It's going to make a problem again, and it's going to cause a lot of leakage in the suspended solids to pass through the filter. So the anthracite would make a little bit of weight on the sand media, where it compacts it. It does a better filtration and prevents any accumulated layer to start moving around inside the tank. Any question?
No, I mean everything is clear so far.
All right. Now, this is the different layers that we already talked about: service, backwash, settle, and rinse. The settle is like a short period of time, like a few seconds, just to make sure that the valves, the automated valve, goes back to their location. Now, Pure Aqua manufactures media filters with different tanks material. Could be stainless steel, could be media, could be carbon steel with epoxy coating, it could be fiberglass. Now, it all depends on the water itself. The water, if it's a seawater, I mean, of course, we have to use, or if it's a very salty water or seawater, we have to use fiberglass tanks where there's no metallic, any metallic material inside the tank or in the face piping or the valves. Now, the accessories that are included usually with our filter, the valves, the media, the internal distribution system, and the face piping for each individual filter. Now, another important thing to mention, like in the media filters in general, like when it's time to backwash, so there are like different methodology that triggers the backwash. One of them is timer based, the other one is differential pressure switch, or an external signal that comes from the BMS system or a building management system, or a manual triggering that the operator would like to start the backwash. Now, from our experience, the best way to do it is like having a differential pressure switch that measures the difference in pressure between the inlet and the outlet. So when the difference in pressure is around 10 to 12 psi, that's going to give a signal to the microprocessor or the PLC control panel to start doing the backwash. Is it going to stop the reverse osmosis? Most probably it will, unless the customer asks for a standby filter where it's not going to interrupt the operation of the entire plant. This is a smaller filter where the control valve is the top mounted, and usually those are used for a small commercial reverse osmosis system. Now, continuing talking about pre-treatment, like we talked a little bit about the chlorination, and we said it's a good idea because it prevents causing damage to the membranes, and it also would like kill any bacteria and viruses. So before that, and then we get rid of the extra chlorine. Now, how can we know that the water is free of chlorine? Like there are devices that we can install, either ORP sensor or chlorine sensor. Like the ORP measures in millivolt, while the chlorine sensor would measure in ppm or milligram per liter. Again, very important thing, the membranes should not be tolerated or exposed to chlorine. It's always a must that we get rid of the chlorine before it goes to the reverse osmosis or nanofiltration membrane. Now, we talked a little bit about the anti-scalant, and we talked a little bit about the benefit of it, and like what we said, the idea of the anti-scalant is very simple. It makes the surface of the membrane slippery, so the membranes will not, or the calcium and magnesium and the other pollen would not stick on the surface of the membrane. That's a very nice diagram that shows the different membranes: microfiltration, ultrafiltration, nanofiltration, reverse osmosis. Looking at the different things, the monovalent ions and the multivalent ions. The mono, like the very small ions, like potassium, sodium, chloride, they will pass easily through the microfiltration. Microfiltration, the only thing really that would do is just reject the suspended solids and the bacteria. So it's questionable about the size of the virus, so most probably will not. UF would reject the virus, bacteria, and suspended solids. Nanofiltration, it will get rid of the multivalent ions, about half-half, because it depends which nanofiltration membrane you are using. Some of them, they would have 50% rejection, some of them would have 70%, some of them would have 80% rejection. Now, nanofiltration is a very good way that people would use it for softening membranes to reject hardness from the water. Now, if the customer doesn't want to use like conventional ion exchange system to get rid of the hardness, the nanofiltration system is your way to go. Finally, the reverse osmosis is absolutely the best way to reject monovalent, multivalent viruses, bacteria, suspended solids from the water. One thing is really good about the reverse osmosis. It accepts the challenge of like changing the feed water characteristic to a certain extent. As an example, if the water is fluctuating and something happened in the water, like some nuclear pollution or something, the reverse osmosis would be able to handle this problem. I'll skip this one because we already talked about it in details. Now, here, let's take a quick glance about the RO system by itself, the main component, what it includes. I'm talking about the RO skid itself. Usually, there is an inlet shutoff valve that prevents the water to pass through the RO system when the RO system is shut down. There's a cartridge filter, which represents the final stage or the final filtration stage before it goes to the pump and the membranes. So this is good, like in case if there's any dirt or inside the chemicals or whatever, so the cartridge filter would be able to capture that dirt. Now, the high pressure pump, like what we said, is responsible of creating the osmotic pressure that's going to be able to pass the water through the reverse osmosis membranes. Now, Pure Aqua, like when we designed the system, we designed it based on 3 years of pump sizing. That means we assume that after 3 years, your membranes are going to get fouled a little bit, and you need more pressure. So we always include about at least 15 to 20% of extra pressure for you so you can still use the RO membranes after 3 years or 4 years. Now we're installing a high pressure throttling valve after the high pressure pump, or instead of the valve, sometimes we install a variable frequency drive, a VFD, to control the pressure of the pump. Installing a VFD here would reduce the speed or increase the speed of the pump, so there is no need for a throttling valve if the VFD option is included. We have another control valve here that controls the amount of water that's going to the drain. If this valve is not located here, you will not get any water on the product side. All the water, more or less, is going to go to the reject side. So again, this one would require like computer projection design to decide on overall recovery, how many stages, how many membranes. So this is all decided by running the computer projection for that specific project. This is how a reverse osmosis membrane would look like. So it would have a membrane sheet, which is a polymer. It has a feed channel spacer, and it has something inside, which is a center tube that has a small hole that collects permeate water. You can collect the water from either side, the permeate water, the good one. Now we're seeing here a little brine seal, the brine seal. Let's assume that we're feeding the water, the raw water here. The water is going to go inside the membranes. The good water is going to be collected inside the perforated center tube. And the bad water, the concentrated water, is going to come from here, the brown, this brown arrows, or the reject. So the brown is going to try to come back here until it reaches to the brine seal. The brine seal would seal it and will not allow the water, the reject water, to go back to the feed water side. Now, Pure Aqua has standard pre-engineered systems that serves industrial and commercial market segmentation. Our systems start from 600 gallons per day, and in the RO200 series, we go all the way up to 18,000 gallons per day. The RO300 goes up to 30,000 gallons per day. The RO400 goes up to 173 gallons per day. The RO500 will go all the way to close to about 1 million gallons per day. Now the water source could be 1,000 ppm, 3,000 ppm, 5,000 ppm, or we can, like what we mentioned here, or we can custom design any of those systems to go all the way up to 12,000 ppm. Now, like the 5 micron cartridge filter, like would look something like this, and the cartridge filter, the element itself would look something like this. Now, anytime you want to change the cartridges, you need to make sure that the system is off. You're going to open the drain valve and the vent valve. Of course, the vent valve would be, you want to open it first, and drain all the water, then open the clamp or the swing bolts, and get all the cartridges out. Make sure to wash the filter from inside, then start loading the new cartridges. Okay, let's go back to the cartridges. When it's time to change the cartridges, anytime when the DP or the differential pressure exceeds 10 to 12 psi. Now, do not wait, because if you're trying to go cheap on the cartridges, you're going to damage the membranes. Do not go cheap on the 5 micron cartridges. Those are very, very inexpensive, but the membranes are very expensive. Now, controllers, they could be either microprocessor or could be a PLC controllers. Whether the customer would choose a microprocessor or a PLC, I mean, this unit is controlling the entire automation of the pre and post treatment of the RO system, including, of course, the RO system. Now, this is how a microprocessor for a commercial system would look like. It would give you a lot of different readings, like running time, hours, ppm, temperature, tank is full, RO is off, auto flush. So it has really a lot of good features. Typical flow meter, like for a small RO, would look like this. Those are like the rotometer style. Now, RO design parameters: conductivity, temperature, recovery, feed water source. Those are, honestly, everybody want to know all those things. So conductivity, we need to know the feed water conductivity. And the customer would like to know the product conductivity, of course. Temperature, we need to know the temperature, because to design a system like with the 77 degree Fahrenheit, or to design a system based on 45 degree Fahrenheit, there is at least about 20% difference in productivity. The lower the temperature, the higher pressure that we need to apply to the RO system. Now, post-treatment, like what we mentioned, it's in certain applications, certain industries, we're required to neutralize the pH. So they want to have the pH around 7, so we would do a little bit of caustic soda or sodium hydroxide. Now, this is like with every application or with every requirement, we would be happy to provide the customer with something like this that gives the customer how many gallons that they would require from antiscalant, from caustic soda, from acid, and all those things. We already talked about the cartridge filter, how it looks like, so we're going to skip this one. Now, loading the media in the filters. Loading the media, you need to start with the bottom media first, so because you're going to load it from the top, and that's going to be the bottom media. Coarse gravel, medium gravel, fine gravel, silica, anthracite. There is something called the freeboard. We have to maintain about 40% freeboard in the tank, because when the filters are in the backwash stage, it's going to lift up the media, so you need something called freeboard, so the media will not escape out of the filter. Like what we mentioned, is about 40%. Now, those are the pressure vessels that they incubate the membranes. A system like this, like when we're going to load the membranes, as an example. In the 8-inch membrane system, we do not load the membranes because the system is going to be really heavy, and we just keep the membranes fresh in the original packaging, where it's going to be maintained, and they don't get dry or they will not get polluted. As an example, this system has a 2-1 array. That means that those two pressure vessels represent the first stage. That second one represents the second stage. So the water is going to come from here, go equally in those two pressure vessels, and it's going to travel like this. Inside those pressure vessels, I would assume there's I would guess about 5 membranes each. And then the reject water from both pressure vessels will feed the second stage. That means the quality of the water that's produced from those two pressure vessels would have a better quality than the second stage. The reason why we have 2 stages, so we can save water and achieve higher recovery. So 1, 2, 3, 4, 5. So I guess that's right. So it has 5 membranes. This is how it goes. That's the first stage membranes, and this is the second stage membranes. This is what we call the thrust cone. So because every time the system starts and stops, there is going to be a little bit shifting inside the membrane. So it's going to maintain the membranes, they don't move a lot. There is something called permeate adapter like this, and there is something called interconnecting adapter, which is like this. And this is what we call the end cap adapter. So the end cap adapter is part of the pressure vessel. So this part and this part is part of the pressure vessel. And this is the thrust cone is installed on the opposite side. So when the flow starts, you're going to make sure that you install it at the end of the flow, not at the beginning, at the end. So the water starts here, because that's where the water going to push the membrane. So it protects if there is any hammering. Any question?
No, I mean, I'm really interested to, see these schematics because it clears all the questions. So perfect job.
Okay. Very good. Okay. So that's how it looks like when the membranes are installed and the pressure vessels are sealed and the end caps are installed. So here we come to a conclusion if there's any more questions about the brackish water reverse osmosis systems. If not, we can seal this session.
Just a quick question regarding anti-scalant selection. So how do you select the most optimal anti-scalants? Is it based on your I'm assuming it's based on your water chemistry. So
exactly. Like now we always look like if what is the foulant that we are trying to prevent from harming the membrane? Is it just hardness? Is it silica? Does it have some like iron, manganese? So it's all based on the water chemistry. And silica is one of the hardest one to clean if the membranes are fouled. So it's always good to choose like a good anti-scalant company and do not go cheap, of course. Like comparing those to like some like cheap quality anti-scalant. So again, like you don't want to go cheap on the cartridges, and you don't want to go cheap on the anti-scalant that you are using, because honestly, membranes they represent about 30% of the cost of the entire plant. So you don't want to ruin your investment by just trying to save like nickeling and diming on a little chemicals or cartridges here and there. Good question.
Yep, that's fair. That's fair. Perfect.
All right. Okay.
Okay.
So now we come
Thank you
to
so
an
much.
end, and thank you so much. And we'll see you again in the next webinar. Thank you.